So good afternoon to all. So it's nice to see you. And I thank my postdoc advisors Nanita Dasgupta and Amitava Dasgupta for introducing me to enter into GaN devices field, because my PhD topic is different. And and I'm thankful to my research advisors Jean Christophe Nelladambi and Rafael Some for their collaboration with them. So the title of the topic is Trap Parameter Evaluation and High Temperature Reverse Bias Stress Effects on GaN-based HEMTs. So currently, by this time last year I joined at IIT Dharwad. So here I am briefly summarizing what are the works I have done in this last 1 year in collaboration with XLM Laboratory. So my current research interest is trapping effects on GaN-based HEMTs and silicon carbide power diodes and transistors, so particularly MOSFETs and BJTs, and semiconductor radiation detectors, neutron and gamma ray detectors for nuclear applications, and trap characterization in devices by using deep level transient spectroscopy. Yeah, so the content of the talk is introduction and DCT and Y22 measurements at different drain voltages and even as well as different temperature also. The objective of the first part is to estimate the zero field activation energy by using measurement and some fundamental TCAD simulations. Then high temperature reverse bias stress effects on the static and dynamic characteristics. So introduction, I think many people talking about gallium nitride is popular. Gallium nitride HEMTs are attractive for power applications and RF applications. So here the depletion mode MOSFETs are widely used for RF application because of their high current density. So it is MMIC technologies or RF power amplifiers. So it is widely used. So it is designed to provide high linearity, high power output efficiency and high output power as well. So generally, I think to reduce the vertical leakage current and punch through effects and to improve the breakdown voltage and to confine the 2-deck in the electron gas, like in the 2-deck channel, we should intentional dopants like compensational dopants are intentionally introduced, like iron or carbon generally it is introduced. So it is making the buffer layer more resistive such a way that it is reducing the buffer leakage and increasing the breakdown voltage, and even some of the TCAD simulations. So in theoretically, conventionally, people say that whenever if you are growing gallium nitride buffer layer, so unintentionally some dopants may be introduced, and maybe the doping concentration, background doping concentration in the range of 10 power 16 per centimeter cube. But still, in TCAD simulations, I am not showing here, but just like a basic fundamental TCAD simulation, it is like if you are not considering any doping in the buffer layer also, you are getting some leakage current path. So it does not necessarily that because of the background doping you are getting leakage current. So to make the buffer layer behave like a semi-insulating material, so these dopants are introduced. So we are because of these compensational dopants, we are getting some benefits. At the same time, these compensational dopants will introduce deep level traps inside the band gap of the gallium nitride material. So it will affect the it will introduce the deep level acceptors. So during the dynamic operation, so mostly it will affect the drain current. So that is called current collapse, the current difference between the static current and pulsed IV or RF current. So in addition to that, it will these temporary trapping behavior, it will affect the RF and microwave output power and restrict the maximum available output current or power added efficiency. So at the moment, drain current transient spectroscopy and low frequency output admittance are the widely used techniques for characterizing defects in the gallium nitride transistors. So already in the morning, Professor Nelladambi, he has mentioned about these characterization techniques. So from these two measurements, we can easily extract the activation energy and capture cross section, and the simplified model is derived. So basically, we know the doping profile in the buffer layer, but what are the active dopants, like ionized dopants are affecting your device performance? That is more essential. So that's why the model is the simplified model we derived. So to estimate the two-dimensional 2-deck reduction during the power switching, like RF switching operation. So this talk, always whenever if you are doing some characterization, so always you are not getting the exact trap activation energy. Okay, so the trap activation energy may be 0.6, for example, you may get 0.4 or 0.5. So you will not get the exact activation energy by because of self-heating effects or maybe pull Fresnel emission or field assisted emission. So to incorporate these effects in the simplified Arrhenius relation, so we can extract the exact zero field activation energy. Zero field activation energy means the activation energy, it is actually there is no field. So it is purely what is the barrier, what is the actual the barrier difference between the for example conduction band to the trap level or maybe valence band to the trap level. So that is the objective. So this is the general thing, electron capture and electron emission. We know that the electron kinetic energy increases towards top side of the band. Okay, so this is capture process. So capture process generally does not require any thermal energy, because you see that the electrons are higher kinetic energy at the conduction band. So if you are having a trap level so that is unoccupied, so that can easily capture the electron. So the reason is, again, it is defined by the Fermi levels. Okay, the trap level should be below the Fermi level, then it is having the more probability to capture the electron from the conduction band. So it does not require any thermal energy. So the capture rate, it is depending upon the free electrons in the conduction band and the capture cross section. Your capture cross section is larger, your capture rate will be larger. So it is having weak temperature difference. Even capture can occur at low temperature or maybe middle temperature also. So it is not purely depending upon the temperature, but emission process is purely thermally activated process, because there is a trap level, okay, and the trap level has to emit it to the conduction band. So it needs a kinetic energy to move from the trap level to the conduction band. So it needs a thermal energy. So that is defined by the equation. So that emission rate equation, so that is related with the temperature, and it is depending upon the trap activation energy. If the trap activation energy is deeper in the band gap, it needed more thermal energy to emit to the respective band. So in this case, we are considering electron trap. Okay, so this is a general behavior, and the trap activation, this trap emission rate, it is depending upon a temperature, and it is depending upon the electric field. If there is an electric field is there, so your thermal emission rate will be accelerated by the electric field. Okay, so because of that, from the Arrhenius relation, you will get the underestimation of thermal activation energy, and maybe that's why we are focused to calculate the zero field activation energy or the actual trap activation energy for particular trap. So basically, it's a buffer trap only. So this is pull Fresnel emission. You see, for example, this is the actual barrier. Okay, so this is the barrier for the trap. Okay, so if it is a normal case, it needs this much energy to emit to that side, and you can see this, the electric field is towards this side. So it means that electron drift should be opposite to the direction of the electric field. So because of this electric field, this barrier layer is this barrier height, it's typical to the Schottky barrier height, maybe analogous to the Schottky barrier height. So there is a reduction in the potential barrier. So that is defined by delta pi. So that is similar to the Schottky barrier lowering expression. So the apparent activation, your actual trap activation energy is E naught. So you are always estimating the apparent activation energy, that is reduced by E naught minus beta of square root of the electric field. Then there are some other tunneling mechanism, but generally it will occur at very high fields. Okay, so mostly these devices are operated in conventional RF operations, so the fields are not very high. If the fields are very high, there may be a possibility of phonon assisted tunneling. So that is it is actually if the phonon assisted tunneling is just, it will get some kind of thermal energy. So when the barrier is triangular or something, then it will tunnel. Okay, so that is PAT, and direct tunneling is it will occur at very high temperature, electric field. So there is a direct tunneling. So we are neglecting that part. So we are assuming that only pull Fresnel emission is dominating in the HEMT structure. So your emission rate equation will be changed according to this expression. Okay, so we are referring that paper. So based on that, this work is done. Then self-heating effect. So in a normal case, we are doing the wafer level measurement. We keep the sample at the probe station or something like that. So we are always measuring the sample chuck temperature. Okay. So but actually, because of the self-heating effect, your channel temperature may be higher than that. So you are assuming that your base temperature is 300. Maybe because of your self-heating effects, your channel temperature may be more than 350 or 400 Kelvin. So because of that, whenever if you are doing the if you are not correcting this temperature difference in the Arrhenius relation, you will underestimate the activation energy. So that's why the equation is simplified. Okay, so this is the actual temperature. Okay, so delta T is the temperature difference between the base temperature and the channel temperature. Okay, so by using a ticket simulation, we estimated the channel temperature. Then accordingly we incorporated the temperature difference. Then we modified the self-heat. We included the self-heating effect for calculating the Arrhenius analysis. In addition to that, we estimated the electric field profile from the validated IV characteristics. Then we have done the measurement at different drain voltages. So we plotted electric field with respect to your activation energy, apparent activation energy. So I think from the slope, from the intercept, you can calculate the zero field activation energy. So that is given in the next slide. So this is the structure it is taken. So it's a typical GaN structure. So that is indium aluminum nitride. So this is advantage, I think yesterday we discussed. So it is lattice matched heterostructure, high spontaneous polarization, and it is having thin barrier layer, and the gate length of 0.12 micrometer and gate width is 6x50. So earlier we have done some so here the conditions, the iron doping profile means we have not exactly implemented the iron doping profile, just the trap concentration, iron introduced trap level concentration is varied. Okay, it is under equilibrium condition only. So earlier we have done the simulations assuming that our doping profile, your iron doping iron related trap concentration is uniform across the buffer layer. So that we considered like that. Even we got a good agreement, like not only us, like in the literature also many people are done like that. But actually when you are looking at the actual iron doping profile, it's not uniform across the buffer layer, because if the doping, if the iron doping is larger, means iron induced trap level density also larger. So once the trap density is larger near to the two-dimensional electron gas, so it will reduce the mobility and it will reduce the NS also. So that's why intentionally near to the channel your iron doping will be lower, then it is increasing exponentially. So a deeper buffer layer, so it will be in the range of 10 power 18 per centimeter cube. So even if you are simulating a uniform dope one condition, and if you are doping with this non-uniform doping, you will get a better performance. Like the leakage, if you are seeing the buffer leakage current, even though the currents are very low, but you can see this kind of configuration, you will get very low leakage current. Okay, so even they are parasitic currents. So here what we have considered is, so the iron doping is near to the channel. So there is in the channel layer there is no traps. So near to the channel it is about 3 × 10 power 16. Then it is increasing exponentially. So at the depth of 0.5 micrometer it is reaching 3 × 10 power 18. Okay, so beyond that depth, so it is constant 3 × 10 power 18. Even like I think in carbon doping also it is like that, but it may not be vary with this kind of exponential behavior. It may vary with the step. Okay. So maybe it is constant for some region, then it will rise. Okay. So this is the ionized doping profile. So the first one is the total trap concentration we have considered according to this condition, and then second condition is ionized acceptor trap concentration at equilibrium condition. Okay, VGS and VDS is equal to 0. So as compared to the earlier case, if we are considering the uniform doping profile, so it may be initially it is higher, then it will decrease, but here it is just initially it is rising, then it is falling off. Okay, anyhow it is depending upon the compensation behavior. So then, so this one just we validated the IV characteristics by using the standard parameter adjustment and other things. So here we estimated the thermal resistance by simulation results. Okay, so you can estimate the thermal resistance by using pulsed IV measurements. Okay, so I think in XLAM lab they have already demonstrated that. So in this case, we have extracted the thermal resistance by using simulations. Okay, so what we have done is we have put the gate voltage is 0, drain voltage we varied. Since the IV is already validated, so we are calculating the channel temperature for each power dissipation. Okay, so each power dissipation is simply the current, what is the current you are getting, and what is the drain voltage you are applying, just a multiplication of that two. Okay, similarly, if you are plotting your power dissipation with respect to the difference in the channel temperature, your base temperature is 300. Okay, so because of the self-heating effects, you will get a rise in the channel temperature. So that difference again, so it is once you are increasing the drain voltage, so your self-heating effect will be more dominant. So that's why you are getting increase in the channel temperature when you are increasing the power dissipation. Okay, and so this one we have already known that your hotspot is located near to the gate edge of the drain side. Okay, so the gate edge located towards the drain side. So generally the thermal resistance we have, it's a simple definition. It is the temperature difference, the actual temperature and the ambient temperature. Okay, then divided by the power dissipation. Okay, so basically we plotted this delta T on this equation. So if you are plotting this power dissipation ID versus VDS, and if you are plotting this delta T from the slope, you will get the RTH. Okay, so here we maintain the unit of Kelvin per unit. So that's why we use the Kelvin per unit. So that is 40 Kelvin per watt. So this value is close to the devices they are fabricated in the same batch. They have done the measurements. So from the measurements also they have obtained this kind of close value, okay, for the thermal resistance. So then drain current transient spectroscopy, this one I think everybody knows about that. So to fill the traps, double pulsing is employed. So there is an off state condition. So in this off state condition, traps under the gate and the trap under the gate drain access regions will be populated. Then immediately you are returning into the semi-on state. Okay, so then you are seeing the detrapping transient or emission transient. Then you are repeating the measurement for different temperatures. So from that you will get the activation energy and capture cross section. So this is the drain current transient spectroscopy, and the below one is derivative of the transient DCT spectra. So the peak position is indicating the emission time constant at the particular temperature, and you can see that when you are increasing the temperature, your emission rate is increases. It means that your emission time constant will decrease. Okay, so similarly that is the another case for this is for VD is equal to 1 volt, and another one is VD is equal to 7 volts. So clear you can see here this is the measured data. So once you are increasing the drain voltage, so your emission time constant is reducing, that is well known. So similarly for these two cases, these RNS plot is made. So from the slope and intercept you can extract the activation energy and capture cross section, and in this equation we have considered this delta T. Okay, so according to this we know the RTH value and we know the power dissipation. So accordingly already the self-heating effect induced temperature rise in the channel, it's already incorporated in the expression. So now our objective is to calculate the zero field activation energy, because already we incorporated these self-heating effects. Even this was demonstrated very long back by Menige, so in 2013. Okay. So zero field activation energy. So we have done the DCT measurements at different drain voltage conditions, and we have repeated for different temperatures. So ultimately you are getting the apparent activation energy for different drain voltages. And we have extracted the electric field profile, okay, the peak electric field profile along the buffer layer. So that is we extracted where is the peak electric field is there. So we plotted for a particular drain voltage, for example, it's a 5 volt. So what is the electric field we are getting and what is the apparent activation energy we are getting. So that we have considered for 5 combinations. So VDC increases from 1 to 5. Then if you are making a linear fit, so according to that expression, so that is your apparent activation energy, E naught is your actual zero field activation energy minus of your pull fractional emission. Okay, so if you take, if you remove the, if you are plotting apparent activation energy with the square root of electric field, so from the intercept you will get the zero field activation energy. So for iron related acceptor trap, the zero field activation energy is close to 0.7. Similarly, the same measurements are done by using Y22 measurement. So in the earlier case, we have populated traps by switching the by making off field voltage. Then we switched into semi-on bias voltage. Then we have measured the transient. But here your DC bias voltage will be fixed. But there is a small AC voltage. A small AC will be overlapped with the DC voltage. So accordingly, it will increase with the frequency. So that's the behavior is just a similar opposite to that. So here the each peak is indicating the emission time constant, and here since it is plotted with the frequency, so once your temperature is increasing, your emission rate will increase. So your frequency also shifted to higher frequencies. That is observed here. Similarly, we have observed pull fractional emission effect here also. So first we are calculating this activation energy. We have incorporated the we have made the correction factor delta T. Then for so here they have for 2 combinations the Renes plot is shown, but actually it is repeated for all the 4 or 5 different drain voltages. So you can see the your activation energy is varying with the drain voltage. So similarly the same thing, like you are getting the apparent activation energy for different drain voltages. Then you are making a linear fit. So from the intercept you are getting the apparent activation energy. So in this case it is a 0.69. So anyhow it is close to that. So the apparent your zero field activation energy for the iron related acceptor trap is about 0.7 electron volt. So we have already by simulation we found that this trap is located below the conduction band EC minus 0.7. Okay, so that's why we are mentioning it's electron trap, and even in the simulation to match with the Y22 and DCT, so we consider this trap as acceptor, then only we are able to match with the experimental results. So so this trap is acceptor trap and it's an electron trap. Yeah, so now some of the studies are underway to estimate the zero field activation energy of carbon doped aluminum indium nitrate GaN-HEMTs. So even here the activation energies are much lower than in generally in a carbon doped material. Your deep level trap, the deep level acceptor is located above the valence band EV minus 0.9 typically, but we didn't observe that trap here. So anyhow, maybe like Professor Nalathambi told, it may be related with the doping profile in the buffer layer or something like that. So there are some recent reports. So if you are getting some reduced activation energy, okay, so it may be a phenomenon of non-exponential behavior. If you are in exponential behavior, you will get a linear fit in the Renes plot. Okay, if you are getting some non-exponential behavior, particularly for surface traps, if the surface traps are behaving like Hoping conduction or some other mechanism, so it will not make a straight line fit when you are doing the Renes plot. So, but here we are getting a linear fit. There is no non-exponential behavior. So it's a exponential behavior. So accordingly, it's considered that. So these traps are behaving following the emission rate as per the SRH recombination theory. Okay. So, but the studies are underway to calculate the zero field estimation, the zero field activation energy for these devices. Then the second section is related with the high temperature reverse bias stress test effect on the HEMTs. So, so even though these HEMTs are like potential candidate for RF and power applications, so their long time reliability has to be studied. Okay, so how much time, how much duration that device can work for a longer period of time. So that you have to identify, but you cannot wait for a longer period of time. So because your device performance will degrade when you are evolving with elapsing with the time. So you cannot wait that much time duration, such a way that it can this device can failure after 2 years or 3 years, like that. Okay, so that's why in industry standard there are some this reliability test. So they are mostly, it is high temperature stressed or like electrical stress. So these high temperature stress will accelerate your failure rate, so that from the it's a standard, I think industry standard, like, so from that you can estimate the mean time to failure, but it is a preliminary study towards the prediction of mean time to failure. So there are some standard like high temperature operating life. So you are keeping the device at operating conditions at high temperature, so that you can estimate the high temperature operating life of your transistor. Similarly, high temperature reverse bias. So even this is much better, because here you are keeping the sample at higher temperature, at the same time you are giving the reverse bias also. Okay, so you are giving both electrical stress and thermal stress. So the advantages, you can identify the root cause of the degradation mechanism. So that's why you can understand the device failure mechanism. So you can improve the reliability of your transistors. Okay. So this is this test is carried out for 0.15 micrometer for iron doped aluminum gallium nitrate HEMTs. So this is a typical AlGaN HEMT structure with 0.15 micrometer iron doped buffer layer and channel layer and barrier layer and GaN cap layer. So the devices on the silicon carbide substrate. So the devices are stressed into off state bias condition. VGS is -7, VDS is 30 volts, and high temperature 175 degrees centigrade for 1000 hours. So even if you are having a cryogenic probe station, so you can do this measurement, because in cryogenic probe station you can operate your device in vacuum condition. So your devices will not be affected by the humidity or storaging conditions. So even with the vacuum probe station also you can do this kind of measurement. So simultaneously after the measurement we analyze the static characteristics ID and IG, and to see is there any new traps are created. So the measurements are done. So the measurements are done by them only. So it's Y22 and DCT, and we have observed some behavior. So that's why we have the simulations are done by 3V lab. So so they identified some behavior. So that we will discuss in the upcoming slides. Okay. So here the stress effects on the static IV characteristics, static IDVD characteristics. So it's clearly see that your drain current is reducing as expected. Similarly, your magnitude of threshold voltage is decreasing. It means that there is a positive shift in the threshold voltage. So this is it's a well known, because when you are keeping your transistor at higher temperature, so your mobility will degrade and your NS will reduce. And because of the optical phonon scattering, your velocity saturation also will be affected. So even though you are keeping at normal condition, so that process, that damaging mechanism has happened, so something may not be recoverable. So that's why you are getting some reduction in the drain current. So then initially we thought of analyzing the gate Schottky diode properties. Okay, so that's why IGVG characteristics are done at VDS is equal to 0. Okay, so we are analyzing the gate current characteristics at VDS is equal to 0. So simply we are analyzing the gate Schottky contact. So here from the forward IV, so there is a negligible current up to 0.6. So the current is constant. So there may be a only possible way is reverse saturation current, and there are two linear regions. Okay, so instead of generally in a Schottky barrier diode, you have a linear region. So that is thermionic emission is dominating. Then after that you will get the series resistance effect. Okay, so series resistance effect, if you are plotting in semi-log scale, it will not be a linear curve. Okay, so it will be like that. Okay. But here you are finding two linear curves. So it means that your Schottky contact, your gate semiconductor contact, it's having non-homogeneous barrier height. Okay, so the barrier height is having two barrier heights. Your metal semiconductor interface is having two barrier heights. So again, so if you are having this kind of two barrier heights, it's difficult to analyze. Maybe since one barrier height is larger, one barrier height is lower. So when you are giving low voltages, current flow through the low barrier height, then after some voltage only it will be equal. Okay, so that's why it's if it is a two barrier height, so generally it is typically observed in silicon carbide Schottky barrier diodes earlier, but now they rectified. But here in this transistor we identified the gate Schottky diode with two linear regions, so two different barrier heights. So their variations are plotted with respect to different temperatures, and here we have seen. So if you see the barrier height variation, so the barrier height variation is increases with respect to temperature. So generally, ideally, when you are increasing the temperature, your Fermi level move towards the middle of the band gap. So in that case, if you are drawing the energy band diagram, so you will get a barrier height lower than what you are getting at room temperature. So that is the typical ideal behavior of a Schottky barrier diode. So here the barrier height is increasing with the temperature. So it means that it is not following the ideal characteristics, it's a non-ideal characteristics. But the ideality factor also increases. Again, this is also non-ideal behavior, because when you are increasing the temperature, your thermionic emission process will increase. So you should your ideality factor should decrease with the temperature. So this is non-ideal behavior of this Schottky gate diode. So after the stress effect, so there is a small increase in the barrier height. Okay, so the physical phenomena behind that we need to see, but there is an increase in the barrier height for the first diode, but in the second diode there is no variation. And if you are seeing the gate current characteristics, there is a small reduction in the gate current, but anyhow it's not very significant. The small reduction in the gate current may be due to your mobility is already degraded because it's a forward IV characteristics, and maybe your barrier height is slightly increased after the stress effect. So because of that, your forward current maybe decreases. So reverse IV similarly for low gate voltages, the currents are came into other side. Okay, so that's why we are not analyzed. So from 2 volts, based on, because here the gate current generally as well reported in the literature, gate current will saturate beyond the pinch off voltage, but in our case the gate current is not saturated even beyond the pinch off voltage. So what we have done is we just validated this IV characteristics, and we extracted the electric field profile from the simulations. Even from the IIT Kanpur also, they have also observed this kind of behavior. So similarly, from the extracted electric field profile, just to be fitted with the basic current equations. So at lower range it is trap assisted tunneling, then Fowler Northium tunneling at higher gate voltages. So, and if you are looking after the stress, there is no considerable variation. It's very difficult to visualize. It's very difficult to differentiate the behavior before stress and after stress. The dotted lines are stressed conditions, so we are unable to differentiate the things. So accordingly, it may be considered that even though in forward current there is a small reduction in the gate current, but in reverse bias there is no considerable variation in the gate current after the stress. So accordingly, it may be considered that the gate Schottky diode quality is not affected after the stress effect. So anyhow, we have done for 1000 hours. So if you are extending for more time, or maybe if you operate at higher temperature, even it may affect your gate Schottky diode. But if you are doing the gate leakage current measurements for different drain voltages, so these are VDS is equal to 0, but if your drain voltages are larger, so but we are observing an increase in the gate leakage current after the stress. So it is considered that, so your gate Schottky diode qualities remain unaffected, but there may be a possibility of, so it's well reported earlier also, once your electric field is exceeding the critical electric field, there may be a creation of defects in the barrier layer. So it may introduce some leakage current paths. So that's why there may be a possibility of increase in the leakage current after your stress effect. Okay, so that's why we are observing increase in the leakage current after the stress. So that all also supported by some of the decade simulations. So this is the output power drift. So R of output power is measured after the stress effect, after the stress experiment. After the stress experiment, we are measured the reduction in the output power with respect to time. So you can clearly see that your output power is reduced or drifted, okay, after the stress condition. So there are some pulsed IV measurement. So in the pulsed IV measurement, the block 1 is unstressed. So after the stress, it is a red line. So it is taken for three different conditions. So the first one is quiescent point is 0, 0. So second one is minus 7, 0. So that time only traps under the gate will be populated, and the third condition is off state condition, minus 7 and 30 volts. So that time your traps under the gate and trap under the gate drain access region will be populated. So, and you can clearly see that in the red color, there is the knee voltage is not visible, okay. There is a smoothing in the knee voltage. So, and if you are drawing the load line, so you can see the reduction in the drain current or knee current. So it is affecting your RF output power, okay. So these simulations are done by the 3V lab at France. So since the objective of the simulation is just to see what effect is introducing this new voltage smoothing. So first we have see, because of this stress effect, is there any trap created in the buffer layer? So that's our objective. So that's why these DCT and Y22 measurements are carried out. So the first figure is Y22 measurements. So the dotted lines are stressed. You can see that the amplitude is decreasing. So Y22 is output conductance. It's related with output conductance. So that is a delta ID divided by delta VD. So in the earlier slide, we have seen that our drain current is reducing. That's why your Y22 peak also reducing after the stress. And there is a small reduction in the frequency also. If you are looking at the DCT measurement, so there is no new peaks are observed after the stress, but there is a small increase in the emission time constant. So if you are so here there is no correction factor and nothing is incorporated, okay. So here after the organized analysis, so the before stress and after stress, your activation energy is almost same. There is no much difference, okay. So it is indicating that there is no new traps are created after the stress, okay. So your trap concentration also may not be increased after the stress. So, but what is the reason for your increase in the leakage current and the new voltage smoothing effect? So in the literature already it's reported that there may be a possibility of creation of defects in the barrier layer. So that's why these TCAT simulations are carried out. So it is taken, it is done by 3V lab, France. This is the 2D cross section of the diode, transistor. The traps are considered in the triangular spatial arrangement with the size of 25 cross 22 nanometer. So if the traps are located here, so that is indicated as drain side of the gate edge, and this is drain side of the gate, okay. And similarly this is drain side of the source edge, and beneath is source side of the gate. So even in this case, traps are considered, some new traps are introduced in the buffer layer also, not only in the barrier layer. The same in the literature, according to the literature, these 3 electron traps are considered, and these traps are considered as acceptor traps, because if there is acceptor trap, then only mostly if it is capturing the electron from the 2 deck, so there is a reduction in the NS. So that's why we have considered acceptor type trap. So the traps are discrete traps, and its density is uniform. It's not varying with the spatial like I have shown in the earlier case, and it's placed at 4 different locations, one at a time, okay. For one combination, one result, another combination, another result. So here, so it's a static simulation. So the objective is to see just which condition is giving the new voltage smoothing, where the new voltage is getting smooth. There are 4 combinations. So the first one is barrier traps under the drain side of the gate edge and drain side of the gate under the gate. So this one. So both the conditions, once your trap concentration is deep level, EC minus 0.93, so there is a clear new voltage smoothing effect. So this is maybe indicating that there may be a creation of some deep level acceptors in the barrier layer. So that is maybe smoothing the transition from ohmic to the saturation region, and it is not affecting the your transfer characteristics. Okay, so this is just to understand what may be the mechanism. So just a simple simulations. It's not validated. Initially, it is validated with the normal IV. So after that, it is simply just the prediction. Okay. So, and if you are introducing the barrier traps near to the source site, there is a reduction in the drain current, but there is no smoothing effect. So accordingly, it is considered that there may be a creation of defects due to the stress effect under the gate edge of the drain side. So that is causing the new voltage smoothing effect. Eventually, it is affecting the output power. So the zero field activation energy for the iron related trap, it is identified. It is 0.7 electron volt. So similarly, the study will be taken out for the carbon doped aluminum indium nitride gallium nitride HEMTs. Then yeah, so the stress effects, drain current is reduced, your gate current under VDS is equal to 0, there is no variation, but your gate current is increases subsequently if you are increasing the drain current. So there may be a creation of barrier layer defects. There is no new traps are identified in the buffer layer after the stress effect. So the simulation studies may indicate that there may be a creation of electrically active traps in the barrier layer that may create a leakage path. So and it is smoothing the transition in the linear and saturation region, and it is affecting the, these are responsible for the RF power degradation. Yeah, so these are the major references. Yeah, so there are some questions. Yeah. Yeah, I think this is the last talk of this workshop.
Thank you, Raja, for this nice presentation. I have two remarks or questions. The first one is transient spectroscopy requires really accurate temperature measurement, and your pulse with high voltage, high drain voltage, and very low negative gate voltage is good because there is no dissipated power there. So my question is there. After this pulse, why do you not use biasing at VDS equals 0 to measure the conductance in the conductance transient, for example, in order to avoid any thermal effect which can affect the accuracy of the energy calculation and capture section calculation? This is my first one. And the second one is related to the Poole-Frenkel effect. It's really a nice effect, interesting. Nevertheless, to exploit such phenomena, the electrical field has to be homogeneous, and we know that in the device, unfortunately, especially at high voltage, near the drain, near the gate, between the gate and the drain, the electrical voltage, electrical field is very, very inhomogeneous. So how do you interpret, because it's really linked to the location of the traps, and actually we don't know exactly. So these are my two questions.
Yeah, so maybe for the first question, I may give a partly answer. I don't know exactly. So if you are doing these measurements at VD is equal to 0, there is no carrier movement now, so you will not get any response. Yeah, maybe we can try, but generally the carrier has to be drifted now to measure the some drain current. So if you are applying very low drain voltage, so even considering this point only, they have initially the measurements are carried out initially 10 volts, 20 volts like that. Even in this case, for the first section, so to reduce the self-heating effects and these what is that? A Poole-Frenkel emission. So we done the measurements. We started the measurements with VDS is equal to 1 volt. So even like nowadays, now they are reducing for less than 1 volts also. And the second question is, yeah, that's true. So generally, it's already the student of Nalathambi Nandakumar Subramani, and not only him, and many peoples, they reported that where the electric field is larger, so you will have a more number of ionized donors, ionized traps, particularly for iron related acceptors. So that's why this electric field is measured along the channel layer, in the buffer layer where the electric field is maximum. So the electric field plotted with respect to the apparent activation energy. So where the electric field along the channel is larger, or the buffer is larger, not channel, close to the channel. So somehow we are approximating. Anyhow, it's a tricky job. So to find the things. Yeah. Any other questions?
Sir, any difference is there for thermal stress and distress?
So thermal stress, if you want to only see the thermal stress, you have to keep the device at high temperature storage studies. Okay. If you want to see only the effect of thermal effect. Thermal stress means you are just you are keeping the sample in a longer period of time. But electrical stress means you are giving some kind of on-state high voltage or off-state voltage. Okay. That's your question?
Yes.
Okay. But in this case, high temperature reverse bias, so that transistors are stored at higher temperature as well as reverse bias during the operation. So both electrical and temperature stress both.
The maximum temperature you keep it as 175, right?
Yeah, 175. Maybe
all the plots you showed is 140 only.
Where? No. This is the devices are stored at 175 degrees centigrade for 1000 hours. So after that, the measurements are carried out at normal condition. Okay. So if you are if the IV is just carried out at room temperature, but the previous condition is it was stored in the it was exposed to the high temperature reverse bias condition. But the normal your IV and IV measurements are carried out at normal ambient conditions. But anyhow, you will have the effect of that storage. And similarly, this TCT and Y22, how it is we measure generally the same thing we measured. But since it is exposed to that stress, so that is the impact of that effect now. So that we are analyzing. So thank you again.
Long live India and France friendship.